And I am going to bring up Stellarium here in a little bit, but remember Stellarium is free. There is an app out there for Android. I don't like the app as well as I like the computer program, but it's cool. This constellation Orion, I'd ask this as a question, but I'm just going to answer it. You can't find Orion here, okay? Orion is not visible. I'm trying to think. If you waited up late enough, I think you could see Orion. I think that's right. Yeah, if you waited up, like if you're a morning person, I think you could see Orion. Now I've got myself wondering. But Orion's beautiful. We're going to see a picture of it here in a minute. Can you guys see the red boundaries here? Okay, those jagged boundaries are kind of like the man-made things around the constellation, so you know that everything in that boundary belongs to that constellation. Can't see all the stars in the constellation, but it's a way of chunking up the nighttime sky. There are, how many, do you guys remember, did I have it on the slide here? How many constellations are there? 88. I thought I had it on the slide earlier. Anyway, there's 88 constellations.
88?
There are 88. The nighttime sky is broken up into 88 chunks. How many keys are there on a piano?
88.
Are there 88?
Yeah.
Okay. All right. That's what I was thinking, there was some sort of connection there. So here we have Orion, Monceros. I don't see much. That's it's a hard constellation to see. We have two dogs. We have the little dog, Canis Minor, and the big dog, Canis Major. Okay. Of course, Canis Major has the bright star Sirius in it. This ... can you see the ... there? This is showing you the winter triangle, which is not up right now. We actually, when we went out for our lab the other day, we saw a summer triangle. I pointed out to some of you guys who came earlier. The summer triangle right now is up. It's got 3 stars, just like the winter triangle, go figure. And the 3 stars are also from different constellations, just like the winter triangle. So here is a figure from your textbook. It just seems brighter than usual. Here is Orion again, the great hunter, with his 2 dogs, little dog and big dog. And this is what you might see in the nighttime sky with Orion. This is what we call his shoulders. This is kind of his shoulders. This is kind of his knees or the bottom of his toga. And these 3 characteristic stars are the belt stars. They kind of around his waist. And then hanging down from these stars is an awesome area called his sword. So this is Orion's sword. Can you kind of tell, like, what color does this look like to people who aren't colorblind? Orange, red, and then like this one's a blue. So right away, you probably already noticed that in nighttime sky, some stars look orange, sometimes some stars look white, some stars look bluish. Okay, and we'll talk about why that is. That's telling you a little bit of what's going on with that distant star. So I mentioned parallax the other day when I was the sun and I was the earth. I put the sun here, and we know that the earth orbits the sun. And those stars still make the same old pattern, even though we're changing. And you might think, well, are changing our position. You might think, well, if we're changing our position, those stars should kind of start to make different pictures as the earth orbits the sun. And the reason they don't is because of parallax. Now I'm going to show you this video, but honestly, everybody has to do this. To show you parallax, all you got to do is, so if you hold your finger in front of your nose, everybody do this, okay, and look into the distance with both eyes open, and then close one eye, and this has got to be close to your nose. One eye, and then the other eye. Did your finger move? So the deal is now, go ahead and take your finger and push, set it as far out as you can, and do the same thing. What would you say about the movement of your finger against the background? It's what? It's smaller. It's less, exactly. If we were to be able to dislocate our finger and take it and move it like even farther, the farther away it is, the less it changes. That's actually can be an angle. When it's close by and you kind of go, you can actually do this. It's a big angle. It gets smaller and smaller and smaller as the object is farther from. What you're doing when you're closing your eyes, one eye and the other eye, you are actually kind of moving here and moving here. You could do the same thing by looking here, looking here. Okay, but we just do it with our one eye and the other eye. By the way the eye doctor, this works with the eye doctor, is the eye, your dominant eye is the one where it changes less when you have both your, relative to when you have both your eyes open. So anyway, that's a dominant. But parallax, the farther away something is, then actually it says at some point it just kind of becomes the background. Parallax. Yeah.
It's like looking down the hallway.
And it kind of
You see the
converges.
hallway like this, and then all of a sudden it'll come to a point.
Yeah.
And it'll be a perfect point, even though you know the hallway
You know
is still the same.
Right.
But down all the way at the end, it's a point.
That
so
is-
it's your parallax.
That is similar. Yep. Here's what this little video says. See if it does it for me. So here the guy is, let's see, how's the guy? We'll see, just watch the video. Okay, so relatively speaking, you can see that what changes most in his field of view is the guy, because the guy is closest. What changes second most are the trees. What changes least, as that photographer, or whatever he's holding, pair of binoculars, moves across the screen, are the mountains. The mountains change least with regard to that guy relocating. Okay, so that's parallax. It also works like if the old-timey cars used to have a needle, not digital, and if you were, there's parallax in that needle too. Like if you're the driver, you see it here against this thing moves, tells you how fast you're going, and this thing has the numbers, versus the person who's sitting over here as the passenger. You see it kind of like what? It looks like they're going faster than they really are. Right.
You also, your height too, your azimuth.
Yeah,
elevation
that's true. Kind of
is
your
different
perspective.
parallax too, for not just east and west,
But-
but north and south too.
But the farther you are from whatever you're kind of moving, then you don't really see parallax. The farther you are, there's no parallax. And that's why as the Earth changes its location in space, orbiting the sun, it basically, all the stars keep the same pattern. I say all the stars keep the same pattern, but they don't all keep the same pattern. Some of them do appear to move against their neighbor stars as the Earth changes its position orbiting the sun. So for instance, this little beautiful orange star right here, it's close enough to see parallax. So let's see if I can draw this. In July, we see this star right here in July. 1, 2, 3, 4, 5, 6. There's 6 white stars that keep the same star field. Then the Earth orbits the sun, and in January, this nearby star is not here. This nearby star is now over here. So that star appears to be a wandering star. That star appears to have relocated. It's only doing that because it's relatively close compared to the other stars. When we talked about, how do you know how far away stars are? And actually, if the star is close enough, we can use parallax. As the Earth is 6 months apart in its orbit, we can see it shift against the background stars. I think the name of the star is the Barnard star, relatively close star. That was the first star that they could actually use this technique. And the more it moves, then the closer it is. The less it moves, the farther it is. At some point, they don't move at all because they're just so far away. So parallax. Back to some constellations. All right. So hopefully you guys see the Big Dipper up here. The Big Dipper has what we call 4 bowl stars. Here's the bowl. I kind of draw a square around the bowl. And then it has 3 handle stars. So 4 bowl stars, 3 handle stars for the Big Dipper. Now the Big Dipper is kind of a good way to orient yourself to the sky. So one thing about the Big Dipper, and we saw it the other night, I didn't emphasize it, but you can take the handle to kind of bend to the bright star called Arcturus. And Arcturus, you arc with the handle of the Big Dipper, you arc to Arcturus. Get Arcturus. So Arcturus actually is in the constellation Bootes. It's a nice, pretty orange star, pretty bright. Don't make me giggle. Okay, so in the bowl of the Big Dipper, we can use the 2 far stars right here. These are the 2 far stars, and if we go up, then the next star we come to is from the far bowl stars is the star Polaris, which right now is our North Star. Is Polaris very bright? No, she's kind of moderately bright. Yep. And as it turns out, Polaris is in the handle of the Little Dipper. So now, the other night, it's hard to make out, especially the bowl, or all 4 stars in the bowl, I think.
You saw 2.
We saw 2. I think, yeah, we saw maybe these far 2, but didn't see these 2 yet. Darker skies, right? And let's see, how does this go? There's actually stories about how, can you see the bowls actually, the 2 bowls, the bowls in the Big Dipper, the bowl in the Little Dipper, they actually kind of pour into each other. Kind of right now, the Little Dipper's pouring in the Big Dipper, okay? So we'll be talking about more about this right now. What did I say? So Polaris would be over there. Remember, this is if this is the sun for the semester, okay? This is our Earth's axis of rotation, and we already kind of talked about this, that it goes like this. 3 months later, it goes like this, and it's always pointing to Polaris. 3 months later, it goes like this. 3 months later, it goes like this. In the meantime, throughout the course of the night, it spins on its axis, right? That's why we have night and day. I guess in the astronomy world, you don't say day and night, you say night and day, because night's your friend. So anyway, that's why actually the sun appears to rise in the east and set in the west. Am I going counterclockwise here? Yes. Yep. The sun appears to rise in the east and set in the west. And also the stars appear to go around the star Polaris. Do you remember what direction they go around the star Polaris? What same direction that the Earth orbits the sun? Yep, it's all about counterclockwise. So the other day I kind of said, if you take your map and if you find the Little Dipper, and in the end of the Little Dipper is Polaris. And if you find the Big Dipper and Cassiopeia, can you kind of see on your sky map how they're kind of across each other from Polaris? And so I like to say that Cassiopeia, the W, and the Big Dipper do this kind of dance thing where they kind of go counterclockwise around Polaris. So, very good. Is Leo up right now did you find Leo on here? If you're ever trying to find, is Leo a sign of the zodiac? Yeah, cool. So here's a hint. On these maps, in most maps, a lot of times they will draw what's called the ecliptic. Can you guys see the dot, 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 the ecliptic? Okay. We'll talk more about that, but the ecliptic is kind of very much associated with the plane of the ecliptic. As I step back here, remember this is kind of the sun. The Earth orbits the sun, and all the planets orbit the sun. Basically, on a sheet of paper, we call the plane of the ecliptic. Okay, so as that turns out, this actually are your zodiac signs. Check it out. So we got Pisces, Aquarius, Capricornus, Sagittarius, Ophiuchus, Scorpius, Libra, Okay, I just kind of counted them off. What's that? Aries, thank you. Oh, don't say Aries. Aries is the ram, right? Okay, good. And if you find the constellation in the nighttime sky, it's just kind of like 2 stars. So you're like, oh, there's Aries. Those 2 stars. But I don't see any Leo here. I would be looking for Leo here. And there's no Leo. I mean, and the reason there's no Leo is the Earth needs to move in orbit about the sun for us to find it. You know what I mean?
Now, would that be on the southern hemisphere you'd be able to see Leo?
Nope. No. No, you can't see it because it's too close at this time of day. At this time of day.
Oh, it's too close.
Yeah, it's too close to the sun. Yeah, I think I'm thinking of that right. All right. Another constellation. So what's the dot, 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 dot? What is that? MW. What do you think is hazy? It's supposed to be kind of haze. It's the Milky Way. Yep, that's the Milky Way. And shown here are those 3 stars in the summer triangle. So they are Deneb in the constellation Cygnus, Vega in the constellation Lyra, and Altair in the constellation Aquila. They make up the summer triangle, which is up right now still. You guys see the summer triangle on your maps? Me too. I'm hoping for real dark skies for our constellation. We'll see. But I love this. Oh my gosh. This is one of my favorite little constellations. Especially the dolphin. It kind of looks like a dolphin. And I also like Sagitta. It's just so adorable. So, and this Vega used to be my daughter's favorite star. I don't know what it is now. So I have a few pictures. I'm going to dim the lights. These are pictures I took at our old house, which before we sold it, we had to get a new roof. I never noticed how bad the roof was until I started looking at these pictures. But anyway, it has a new roof and it's not our house anymore. But the Pleiades, that's the 7 sisters. It's an open cluster. Let's see, head of Taurus. I can't even make that out. Oh, but over here, can you make out, this is Orion over here. And here are the 3 belt stars. Here is the sword, and this must be kind of his corners. I know. You're like, really? This is a photo of, you can kind of see the Milky Way. And here is the summer triangle. Vega, Deneb, Altair. Okay. Wow. I wish I had one to show you. I used to have one to show you, but it got too torn up. It's called the celestial sphere. And you're going to see a picture of it here in a minute, but I'll just kind of describe what you're going to see. Basically, the celestial sphere is kind of a clear sort of sphere with the constellations, the stars of the constellations printed on it. And in the middle, you have the Earth. And that's kind of, it's not the true real deal, but a lot of times scientific models kind of talk about what it feels like. Because it kind of feels like we're in a globe of stars. Okay? That is the celestial sphere. So in the celestial sphere, in this globe, okay, this is the globe, the celestial sphere. In here, in the heart of it, then the nugget is the Earth. Okay? The celestial sphere has things that line up relative to the Earth. So, for instance, we have the Earth's axis of rotation. A lot of times, the celestial sphere, you're going to see the Earth's axis of rotation straight up and down. Earth's axis of rotation, because the celestial sphere is around it. So, if you take this north axis and go ahead and have it from the Earth hit the celestial sphere, that would be the celestial sphere north axis of rotation. You go ahead and take the Earth's south axis of rotation, have it extend out to the celestial sphere, that's the south pole of the celestial sphere. You have the equator extend out from the Earth, and that's the equator of the celestial sphere. Okay, so it's like a ball inside a sphere. So we can kind of think as the Earth rotating or spinning inside the celestial sphere throughout the course of a day to kind of explain why the stars move. Is that the way it works? No. But here's the celestial, it's hard for me to say sometimes. Here's the celestial sphere that I've been talking about. So kind of think of this as that's your celestial sphere, and then those white dots would be the stars painted on the celestial sphere. And so, like I said, you can take the north axis of rotation, that's the north celestial pole, south axis of rotation, south celestial pole. Okay, our equator, this is that right here, extends out. Okay, that is the celestial equator. Now, tilted, can you kind of see tilted to the celestial equator is the, what's it called here? The ecliptic. Okay, what did I say the ecliptic was a minute ago?
23.5.
What?
Is that 23.5 degrees?
It's tilted 23.5 degrees, but what is the ecliptic aside from this discussion? What did I say the ecliptic was? That's what?
The zodiac signs.
The zodiac signs. The ecliptics is the zodiac signs. And the ecliptic is also the plane that the Earth orbits the sun in. Okay? So the plane that the Earth orbits the sun in is actually tilted 23.5 degrees outside of the celestial equator. I know. It's kind of, I have to think about these things and then they make sense. On our imaginary ball, on our celestial sphere, we can go ahead and we can paint little yellow dots. And if I had a celestial sphere, it would have little yellow dots or some way to show where the sun is as it moves against the background stars in our celestial sphere. Not throughout the course of an evening, obviously, but through the course of one orbit, one Earth's orbits around the sun. Okay, it's a complicated model. If you might be thinking, now that hurts my brain. Well, it hurts my brain too. The biggest thing that I will probably test you over is something like this. Do you understand what a celestial sphere is? It's a model of the stars as they are rigidly in a ball around the Earth. That's the celestial sphere. Celestial sphere is oftentimes called a hollow sphere with the Earth at the center. So here's continuing with our ghostly celestial sphere. I'm going to throw some terms at you later. One of the terms that you may already be familiar with is your zenith. Now, zenith has nothing to do with, well, it really doesn't have anything to do with the Earth or the celestial sphere. I could go out here and my zenith would be straight up. That's it. Wherever you are, your zenith, you have your own personal zenith, and it's straight up. Well, I have a slide kind of to show you that. But this particular person, oh, it looks like it could be, I'd have to make it larger, but it looks like they're in the States. I don't know if they're as far north as we are. It looks like maybe a little bit south. Okay, but that's their zenith. And when they look out at Polaris, or the North Pole, they're going to find the North Pole out here. And can you see, okay, two things. If I'm over here outside the celestial sphere, what direction does it look like stars are moving? To me, it looks clockwise. What if I go inside here in the celestial sphere? What direction does it look like they're going? Counterclockwise. I know it hurts my brain. Just go out and watch Nighttime Sky and enjoy it. It's counterclockwise around Polaris. Okay, exactly. Milky Way again, and I feel like we've kind of talked about the Milky Way. I encourage you to use binoculars, look up and see all those beautiful stars that just, it's amazing. But remember that sometimes you're going to see dark bands in the Milky Way, and that's not the absence of stars. Basically, think of that as kind of clouds obscuring the stars behind them. And when we see the Milky Way, we are looking into the plane of our galaxy. So what's this right? What's right here? Black hole. Supermassive black hole. Yep. And then we're out here, kind of halfway between the middle of our galaxy and the edge of our galaxy. So when we look at the Milky Way, it should go from one horizon to the other horizon, just kind of like you see it here. This hurts my brain too. There's a lot of things that hurt my brain in astronomy. But if I think about it, I'm like, that makes sense. As we orbit the sun, we see different stars, and also as we orbit the sun, we see different parts of the Milky Way. You know, so
this kind of off topic, but is there more than one sun in the Milky Way galaxy?
yes, yes and no. The word sun actually is associated with only one star, and that's that one right up there. Okay, but every star can be its own sun to a system of planets. Every star.
So there could be another sun out there with other planets in our galaxy.
Oh yeah, yeah. Most stars have they think it's like 2.5 children. Like most couples have 2.5 children. They're thinking from what they have found with a spacecraft, Kepler telescope mostly, but that for every star we see, it's got 2.5 or 2+ planets. Yeah. And then its own little sun to that side of the planet.
So like the North Star has planets around it?
What's that?
Like the North Star has planets around it?
Well, that's a good question. I should Google that one. Does Polaris that star have planets orbiting it? I'm not sure. Though, if you're Googling it, what you're going to hear them called are exoplanets, like extra or exoplanets around another star. So I'll have to look that up. I think probably the way that scientists have made the bold statement that every star has 2 or plus planets orbiting it is the fact that Kepler went out and surveyed a set of stars, and based upon those statistics, they can probably make that. So I'm not sure that Kepler looked at Polaris, but that makes me smile. Oh no. Instead of hurting my brain, it makes me smile. A few more pictures. Hard to see. So if you go out tonight, the domes are so pretty. We've got 2 domes that house 2 large telescopes, and then a meeting room and a roll-off. There's no bathroom at the observatory, so don't drink a lot of water before you come. That's what I do. Don't drink a lot. But we have a nice outhouse. This is a plane going through. You can kind of see the choppiness. Okay. So I mentioned zenith. So everybody, I never thought about this before, but you get your own personal zenith. My zenith is different than your zenith. Okay. But you can kind of see the dome here over this person's head. That is your own personal kind of field of view. So you have your zenith, okay? And then we kind of start to talk about kind of relative to where you're at. So for instance, this would be north, right? North on my horizon. This would be south on my horizon. This would be east on my horizon. This would be west on my horizon. A lot of times we'll put numbers with those. Due north is 0 degrees, and then we have 90, and then we have 180, and then we have, what's plus 90? 270, then we have 360. Okay. So this is kind of just your own personal space. And then we have to kind of do this sort of thing, okay? So this is your, I think this is a term Barry mentioned. This is actually your altitude. Okay, anyway.
Azimuth and
Yeah, this is your yeah. I learned it as altitude.
Yeah.
So if you're straight up at the zenith, does that look like 90 degrees? Good. Okay. So then this would be 45, and this would be, 20. Okay, what angle would this be with my horizon? 0. Yeah, so we have 90. So we can, sometimes when someone's trying to describe an event, something to look at in the nighttime sky, they'll say, well, it's 90 degrees along the horizon, and then it's up 20 degrees. And you're like, oh, okay, well, I think I can find that. Okay, so they're trying to describe to you in your local sky where to look. So I mentioned the whole degrees thing. You guys told me this was 90 and this is 0, okay? So in the nighttime sky, sometimes we need to kind of say relative, like how much of the sky it kind of, what we say, subtends. So for most people, if you extend your hand, and you extend your hand and you put out your finger, that actually is 1 degree. 1 degree relative to like a whole circle, okay? If you put out your fist, that's 10 degrees. So the Big Dipper is about half a fist. The bowl is about a half a fist. Now, one of the things about the Big Dipper, oh my gosh, have you ever been driving and seen the Big Dipper just hover against the kind of the horizon because it's swinging down? Cassiopeia is up here, Big Dipper's down here, kind of swings around. Like that looks humongous, and then if it's up in the sky, it looks small. Well, it doesn't change size. It has to do with kind of the conditioning of our brains. Okay, it's the same. It's 5 degrees either place. You ever seen the moon looks humongous on the horizon, but up it looks normal? Same diff. The moon, by the way, subtends not 1 degree, but a half a degree. And you're like, I know the moon's bigger than this because this is 1 degree. So a full moon would be a half a degree. Are you sure? Okay. Well, try to convince yourself of it. Make people wonder what you're doing. You go out and you go, put your finger at the moon. So yeah, we just had an eclipse here a week ago, and honestly, related to why we can have eclipse, there's several factors, but one is that the disk of the sun and the disk of the moon, from our perspective, are very similar, the size. Okay, so they're both about a half a degree. Is that true? Okay. So I didn't bring my globe in here, but if you travel to the North Pole, you'd say you're at 90 degrees north latitude. If you're at the equator, you're at 0 degrees latitude. If you go to the South Pole, you're at 90 degrees south latitude. Okay, does that make sense? So latitudes are what we call kind of the great circle. They kind of go, okay, like that around the Earth. Like that. Then we have this longitude. Longitudes go long ways from pole to pole. Okay, longitudes. So lines of longitude have to start somewhere. Okay, and so lines of longitude actually start at Greenwich, England, and then lines of longitude go east. They go east and west, and then they meet again at the international date line. Kind of familiar with that. That's so cool.
Why did they pick Greenwich?
I said, why did they pick Greenwich? I'm thinking it was an early kind of a
Or was it a dream
time,
thing,
date?
or what?
I don't know. I don't know. Good question.
So,
I would like to think it's like a science thing.
You ready for a little? There, Polaris is a yellow supergiant star shining with a luminosity of 25,000 or 2,500 suns.
Okay, it's a Polaris bio.
No,
Does it have any?
It just says Polaris.
No, I thought I meant like a biography. Thank you. Did it say anything about planets?
No, it says it doesn't have any planets.
Well, we don't know that it has any planets yet because we haven't, there's hope.
Right.
So I kind of feel like we've been talking about this already a little bit today. So if you find Polaris, what direction are the stars going to move around it? Counterclockwise, exactly. And so the deal is at, I'm kind of getting ahead of myself, but when you find Polaris, if you go ahead and put one hand out at the horizon and the other arm out at where Polaris is, that angle actually is your latitude. That angle right here is your latitude. We're about 43 degrees north. Okay. So this is to say that if you go up, what latitude is the North Pole? 90. Yeah, the North Pole is 90 degrees latitude. If you're at the North Pole, dude, you got like the axis of rotation just going right through you, right? So if the axis of rotation is going through you, then guess where Polaris is?
Straight up above.
Isn't that awesome? Polaris is at your zenith. So if we go ahead and do the same idea, put your hand up there, just point to Polaris, put your hand out at the horizon, okay, and then what angle do you have? 90. That's so cool. And so, like, navigators, old-timey sea navigators would use these sextants, and that's one of the things a star that they could use to understand how close to the equator, how far they were. Now, if they were south of the equator, there is no south pole star. Not right now. Okay, so I kind of feel like we talked about this already. Oh, what I started to say is, so Polaris is about 45-degree angle above the horizon, 43. So the thing is, you can take a circle, okay, kind of picturing the stars move as the Earth spins. At some point, and by the way, those circles, those are the stars within there we call circumpolar. They're always up, you can always see them. But if your circle gets too big, you're going to bump up against the horizon. And at some point, you make the circle big enough, basically, like I said the other day, you're rising in the east and setting in the west. That's your circle. And then you go behind you, and actually there would be circles. Not full circles, actually, because you run into the horizon, which is these arcs. So there is not a pole star for our south axis of rotation. And this kind of hurts my brain too. So if you were to go down to the South Pole and look at the stars, they actually are moving clockwise. Okay. So here's a star trail, actually in the southern hemisphere, but this is where I've kind of been talking about if you just open up your shutter of your camera, thank you. Open up the shutter of your camera, you can actually kind of see them move. Instead of that, there are some cool programs out there, and they're free. I've played around with them. You can actually just kind of take a bunch of pictures, and then what they do, this program does, is stitch them all together and make the star trail for you. So, okay, there is the celestial sphere, and there's the eclipse. There's the Earth inside. And there's somebody at the North Pole, and that's kind of how they would see the stars move. Let's switch it up. Now we're going to go to the equator. If you go to no, is that right? Yeah, we're going to go to the equator. This hurts my brain again. I don't like how they did this. If we go to the equator, if you look for Polaris, Polaris is actually going to be on your horizon. On the equator, Polaris is on your horizon. If Polaris is on your horizon, then actually you're basically going to just kind of see some arcs. Arc, 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 arc.
See, when I was in Iraq, the Big Dipper was straight up and down. It wasn't canted or nothing.
Okay.
It was straight up and down. The top of the handle was like straight up. So, Polaris was over, like, real close to the horizon.
Yeah, yeah.
Instead of being where you normally see
right,
it.
45, it was close to the horizon. Yeah. Good. And this is kind of how we are. This is kind of how we see Polaris. Oh, yeah. Okay. So polar bear, North Pole. And we kind of said at the North Pole, you guys told me Polaris would be right up here, and we'd see a circle. And the reason that polar bear is going to get kind of dizzy is if you take that circle, make it bigger and bigger and bigger, as it meets the horizon, as he's looking at the horizon, he's basically going to see stars go like this. Isn't that neat? I know. This one is at the equator. And at the equator, we said that Polaris is going to be on your horizon. Okay, and you're going to kind of see circles go counterclockwise, counterclockwise, counterclockwise. Well, that's looking north. But if you look due west or due east, you're going to basically see star trails go like this. Okay, and then they'll go like this, and they'll get smaller and smaller and smaller arcs until you get to the South Pole. North Pole, South Pole, so little arcs, little arcs, little arcs, like that. And this is what we see. So this is kind of showing you, you see the two dippers up here. Now the dippers, the Big Dipper and the Little Dipper, they aren't constellations, they're what are called asterisms. They're kind of a subset of a constellation. So here you see the Little Dipper swinging around, and I think each is 2 hours. So here, 2 hours later, 2 hours later, and 2 hours later. You can kind of see it going counterclockwise. And you can see the Big Dipper going counterclockwise. In the southern hemisphere, there is no South Pole star, but in order to find the region of South Pole, what they do is they take a constellation, and I've not been there yet, called the Southern Cross, and you take this and you go about approximately 4 lengths in, and you'll get to where the rotation is. So, and like I said, don't let fret you too much, but rotation is clockwise there. Are we almost done? So I'm going to go ahead and make this assignment because I think we've talked about it enough, but I'm going to come back and look at those last 2 slides for this part. This says, is the ecliptic the same as the celestial equator? I don't need to write your answer for you, but a few slides ago, remember we said we saw the celestial sphere, the celestial equator, and how is the ecliptic? Okay, it's tilted. So they are different. So just think about those things. It's good for you to think about those things. And let me know what you think. Okay?
Is this due on Monday?
This will be due, oh, we're not having class on Monday.
Oh, duh.
Yeah, I keep forgetting too,
Come
Wednesday.
here on Monday.
This will be due Wednesday.
Yeah, I'll be helping my little brother.